All right. So today we're going to be talking a little bit about circular motion later. We're going to start off with some friction. I need to hit a button here really quick. So we're in chapter 6 on about a page 100. Maybe we could start with the screen share here. But so maybe by the end of today, we can understand a little bit about this. That's our goal. All right. That said, we need to start by doing some friction problems. We only talked about it very briefly, so we need to do a couple of those before we move on. So let me start with the screen share. Okay, any day now. There we go. All right, and so this is actually page 99. So on page 99, remember this was the stuff that we were going to worry about for friction. Also, I know a lot of you are coming in at 4:35. If you guys could try and get here at before 4:30, that would make it easier for me to start on time because there's bells going off in my head while I'm trying to do the basics. So basically, do a better job of getting here on time, even if that means you got to wait for me a little bit. And those of you that have been getting here on time, thank you. But those of you that are getting here late, it's really 5 minutes a day adds up to more than an hour over the whole course. So more than 2 hours. So get here on time when you can. All right. Try to sit there in the waiting room and I'll be ready. All right. That said, here's some friction cases. So we talked about if two objects are in relative motion, we're going to use this equation. If two objects if one of the objects is on the verge of slipping, great. Pablo, get here on time next time, please. Right. It's really annoying for me when I've got 10, 20 people coming in late. So just try a little bit harder, everybody, to get here on time. All right. Now, when we don't indicate, it's very disruptive for me when I'm trying to talk and people are constantly trying to add to the Zoom room. So get here on time. It's 7 minutes in. All right. So, and you can see this is what happens. I get distracted. I get off topic. We've wasted 7 minutes now. It's really irritating. So, all right. If two objects are in relative motion, you could use this equation. If one of them is about to slip, you could use this equation. Watch out. If things are not on the verge of slipping, we do not want to use that equation. We could use this equation, but it turns out that's very useless, right? That doesn't help you. Now, friction, which way does it point? Let's go to the summary. Consider the tendency of an object to move, and remember that friction should point opposite that tendency to move. And remember, we're talking about relative motion. So for example, in this one with blocks 1 and 2, there's different friction directions in this problem. We'll get to that one maybe in a little bit. All right. So let's go on. I do want to say one more thing. If you have on the bottom of page 100, update the question to read this. So 6.3.5, the bottom of page 100. I think we talked about this one last time, and I didn't want to use M2 minimum. I meant to say F minimum to cause slipping. So that makes the problem make a lot more sense. It makes the solution make a lot more sense, and I apologize for that. That said, these were to help you figure out the direction of friction. And then let's maybe look here for a good problem to do. Let's try 6.17. Now, you might notice this problem is going to be pretty nasty. So later on, if this is confusing, you could try 6.18 and a half. But let's do this problem, 6.17. Now, I am going to draw the FBDs, and then I'll turn my board around to you guys. But so I'm going to move this so I don't get stabbed. All right. So go ahead and write up what you think you should draw, and I'll get caught up here. Read the question, get a feeling for it. got an angle theta, got some blocks. We know mu static equals 0.5, mu kinetic. Remember, those are not friction. Those are coefficients of friction or frictional coefficients. All right. And just writing some notes here. We want the minimum zombie force to slide up. Let's just start with that question. All right. So now I've got the problem on my whiteboard here. All right. And so the first thing I might do is give this force a name. So I might as well call it F. And the idea is we're looking for that force. All right. So in this problem, which friction case applies? Should we use mu kinetic? Should we use mu static? Or should we not use either of those?
Use kinetic because we want it to slide up, right?
That's what you would think. Turns out that's not right. So this is the key word. If we want the minimum force for it to slide up, there's a trick. If it was actually sliding up, you're absolutely right. We would use mu kinetic. However, the trick is when you see this wording, I want you to think two things. Set acceleration equal to 0 and set friction equal to mu static times the normal force. So we know it will slide if you exceed this frictional force. So this is the largest possible friction force that one could apply. And that's going to happen if you apply more than the minimum force. It will slide, it will accelerate, and we would use mu kinetic. Again, if you applied more, so if we assume these conditions, we'll get a value for F. If you apply a larger F than that, A would be non-zero, and this would be mu kinetic. So that's kind of the reasoning. Does that make sense, Alonzo?
Yeah.
Right on, right on. And so that's the trick. Anybody else have questions about that?
So is it kind of asking like where it's about to start slipping? Like that's what we're finding?
Yes. So said another way, it's on the verge of slipping. So this is very confusing when you're first starting. You're like, you said it's slipping. Yes, true. I said, I want the minimum force to cause it to slide up. So first what I do is assume it doesn't slip. That means it's about to slip. Good, Jake?
Yeah, that makes sense.
Okay. Got it. All right. So in this case, we could now do some FBDs. So what should the free body diagrams look like? Go ahead and think what they should draw. You could obviously check with the solutions, but give it a shot. So how many FBDs might be appropriate for this picture?
2, 3.
2 or 3 is a good answer. So obviously there's 2 blocks. We would expect 2 FBDs. What's the third one you were thinking of?
A system.
You could also do a system because they move together. And so for practice, let's do all 3. Okay.
I have a question.
Oh, go ahead. Yeah.
Could we represent it as just one free body diagram? Like if we view it as like one giant block?
That's the system. Absolutely.
Okay.
So that would be, we could do each block separately or the system, right? So absolutely. Let's go ahead and draw it. And then I know this seems a little bit crazy, but 2M is over here. So why don't we draw it over here? M is right here. And then this is kind of in the way. Let me move this up. Let's do FBD of the system over here. All right. So which one do you think will be the easiest? There's many correct answers for this, so go ahead and unmute and say what you think. Which one do you think is the easiest?
System.
All right, so
System.
give me one force on the system.
Friction.
Friction, which way?
Going to the left.
So like this?
Yeah.
I would say no.
Going down the plane.
So now I know that's probably gone, and I know he does that weird stuff where he rotates it, but let's not do that. So if that was what you're saying, then G Money, you're fine. Okay. But for the rest of us, let's think of this as friction going down the plane. And the second half of today's lecture, when things are going in circles, it's going to become more and more important to draw things as they are actually oriented in the figure. Okay. So the words that we could use are up, down, left, right, up the plane and down the plane. And those words, and you could also say perpendicular to the plane. That can help you communicate. All right. So I think G was on it, but yeah. All right. Let's keep going. What else? Give me another force.
We have F going straight to the right.
Okay. Got it. Now let's not try to get this perfectly to scale. Let's just get it done. There's F. What else? Somebody
Normal
else.
force,
Normal force. All right. Which way is that?
perpendicular.
Yep. You'll notice this if you start doing this over and over again. The normal force and the friction are always perpendicular in these pictures. Oh, somebody put one in the chat. Let's see what they put there. Yeah. Okay. Gotcha, G. I can't help it. If that's how you like to do it and get the answers right, cool. All right. Anything else?
The combined mass,
Okay. What do you mean?
3m and m combined. So you'd have 3m going down.
Not 3M.
You'd have m total,
3mg.
3mg.
Right? Because M is not a force. You got to write 3mg.
Gotcha.
And you probably knew that, but I'm just making sure because I've seen it on test questions a lot. So remember, M is not a force. Mg is a force. Nice. Okay, and we see there's a logical, we could split this up like this. This angle right in there with the dot is going to be theta. We're good to go. All right, so what's the next one you want to try?
Wouldn't the force have to be split up too?
Oh, yeah, you're right. This one's horizontal. Sorry. So this angle in here I could tell is theta. Right? Good call. Thank you. So in this case, notice every other angle is theta. Or because I drew my triangle with a skinny angle, you can just look at it and see which ones are theta. Right? Okay. Good job. Thank you. How about FBDM? What's one force acting on FBDM?
MG.
We have.
mg, I got that.
We also have the normal force between 2.
Okay, a
and
normal
M.
force between 2 and M. Which way does that act on M?
On M, that will act up the plane.
So what's a good name for that? Should I call it N or something else?
And well, I guess I'd call it N21 or N12.
Yeah. So the idea is this normal force is not the same as that normal force. So they shouldn't have the same name. Shouldn't have the same name. All right. What else? Is there friction on this block or not?
If it's on the verge of slipping, there's no friction.
If there's the maximum possible friction when it's on the verge of slipping.
Okay.
So if it's at rest, it's quite possible. What if you apply just a little bit of force, right? Then it's possible there could be, in some weird situation, absolutely no friction if the zombie balances out what friction is required. However, this zombie is just about to get it to slide upwards. If he pushes any harder, it will slide. That means the friction is present and pushing down. Does that help?
Yeah.
All right. Now, in this case, what's a good name for this one? How about friction? How about just friction 1? Because it's not the same as this. This is the total friction from both blocks. So why don't I call this one friction 1 for right now? All right. Anything else? What holds it up?
The ramp, normal force of the ramp.
Yeah. So let's call that normal force 1. So notice we've now got 3 different normal forces. This is the total normal force from the ramp. This is the normal force of the ramp on block 1 only. This is the normal force between the 2 blocks. Yeesh. Did I forget anything there? I think that's it. What about the force capital F? Should that be on there?
No.
Not from
No,
M2.
well,
No.
because of the
That force,
N21.
yeah, that's basically incorporated right here. You're going to push this way horizontally on this block. As a result, that block pushes up the plane on here. So as a result of all these complicated forces, that one's going to move this way, being pushed by that normal force. But this force is only touching block 2, or the system, which includes block 2. All right, so let's go over to here. What are we going to get here? Well, I know 2mg. I'll do that. Two mg. Hey, I know there's a force F. I got that. All right, what else?
And 1 on 2,
And 1 on 2. Which way?
diagonal to the bottom left.
Yeah, down the plane. And now we could call this 1, 2, but remember the magnitude is the same as this one. So we could just keep it the same. So call both of them N12 or both of them N21. Doesn't matter. What else?
Frictional force the same way.
Yes. So is that F1 or is that F?
F2.
Yeah, it's a new friction, F2. So we got 2. Oh my gosh. Anything else?
Normal upwards.
Yeah. Notice the normal force is different. So we have to keep track of these somehow. And again, we're going to split this up. You could tell that this has got to be theta. This has got to be theta. I'm going to pause here and see if there's any questions. So let's get in on these FBDs. Any questions on that? In this case, remember the acceleration is 0. Let's go take a look at the solution, see if there's anything that jumps out now. That's the hard part, right? Obviously, you have to be able to write the force equations too. But this, notice I drew this one to scale. I would not expect you to figure out how to draw them to scale. So at some point, these get so complicated, you could just draw all the arrows the same size. But you could see this, you could see the force equations. If you're curious, you could do some algebra and figure out the total force. We could figure out the normal force between them. So we could figure out all kinds of weird stuff there. The rest is just algebra. This is kind of what we need to focus on. So see if there's anything in there that you have a question about. Maybe take a second and make sure you feel okay with the force equations. I line up the objects the same order that they appeared in the actual diagram. I also label them so I can keep track of them. Furthermore, I make sure I put subscripts on the masses, right? Or make sure you use M and 2M, things like that. All right. You draw a skinny angle to make sure you could tell where theta is without having to do a lot of geometry. I labeled that the acceleration is 0, rotated the coordinates. All right. So the rest of it's just algebra. You could do that on your own. Okay. And then let's take a look at another one. Oops, let's go to here. So that's a pretty good one. Now, if that was really confusing, look at 6.18 and a half. This is the one without the angle. You could try that again. All right. So that's a good problem. Let's look at 6.19 now. Actually, oh, you know what? I did 6.19 in the last class. Let's spice it up a little. No, let's do 619. This is just such a good problem. We should do this one. Sorry, keep changing my mind on you guys. This is 6.19. It's probably on page what? 103. 103, 6.19. Okay, I'm going to just get this new problem drawn up, all right? Basically the same as chapter 5, but you have to do friction as well. And the friction ends up taking up almost as much time as the whole problem because you have to think carefully. So now we're going to 6.19. Got block 1 on top, block 2 on bottom, sitting on a level surface. And apply some force here, F. Ooh, this time it looks like oh, I see. We'll read in the question. This one, it says it accelerates to the right. I'm going to get that in my picture right away. I'll show you my whiteboard in a minute. And then I've got some coefficients. I'm going to write that down. All right. Then we're told they move together as a single unit and we're going to do some forces and stuff. All right. That's great. What might this look like? Well, all right. Even though this isn't sliding, you could imagine this is a surface, right? So you could see that there's a block sitting on top of here, right? And I'm just going to push it along this surface and the upper block comes along with it. This is not outrageous to think of. This is completely normal. We do this stuff all the time, right? So the idea is as I push it forwards along the surface, we see the upper block comes along for the ride. Very reasonable situation. All right. Here's what I wrote down. Maybe you wrote down something else, but whatever. Okay. So in this case, which friction case applies? And notice there could be more than one case in this situation. Maybe let's bring up the problem on the screen again so we could read the words.
Would it be kinetic for the bottom and static for the top?
Okay, so there's kinetic down here. So you're saying use mu kinetic times the normal force?
Yes.
And then up here, what would you use?
Static because it's not moving because it's on top of the block.
So mu static times the normal force. Is that what you're saying?
Correct.
And that's wrong.
Shouldn't it be less than because it says M1 does not slide relative to M2?
So it doesn't look, this is, I tried to trick you, Jesse, and I succeeded. The idea is, look at this. In question part C, your analysis would be valid because that says determine the maximum possible F. However, for part B, nothing in the problem during part B tells us that. So that's where we have to be careful. In general, static friction applies, but the equation for static friction is mu is less than or equal to mu static times the normal force. In this particular problem, Kc uses the equal sign. Part B uses the less than symbol, and we could see that when we do the problem. And so it turns out we do not want to assume blindly for all parts of this problem that we can use mu static times normal force. Is that good, Jesse?
So if it says maximum possible, then you use the equal sign. But if it doesn't say that, then you use less than or equal to.
Yeah. And notice in the last problem, there was minimum. Remember that? So some kind of extrema. So if it says maximum angle before it starts to slip, or minimum force or minimum mass where it remains at rest, or things like this. So those are the kind of issues that we have to look for in the wording. If it says it's just about to slip in some novel way in the wording, minimum, maximum, about to slip, it could even say on the verge of slipping. Is that good?
Perfect. Got it.
Yeah. So watch out for that wording. So we'll assume Jesse was actually thinking about part C. That's why he got it right. There we go. Right. Okay. So in this case, hey, let's do some FBDs. All right. So in this case, well, we're working horizontally. Why don't we just say FBD1 here? FBD2. Is it okay to use a system or not in this case?
Yes, and it even says to make it.
Yeah, because we have this move together as a single unit phrase. Whenever that's the case, we could do a system. All right. So in this case, let's look right here. Block 1, let's go in order. Well, there's a normal force up, right? What do you want to call this normal force?
N.
I would call it N12, only because it's coming from this interface right here between 1 and 2. So that keeps with our standard convention that we're using on every other problem. Could you call it? What's that?
Would there still be an actual normal force upwards besides the N1 on 2?
No, that's it. The normal force. What's holding up block 1? The book. Right? The normal force between the book and this drive is what's holding it up. Right? Not my hand. I'm holding up the book. The book is holding up the drive. That's why I'm going to call it N12. Is that cool? Hopefully that's good. Okay. What else do we have here? Well, there's going to be an MG. I'll get that. Is that it? And maybe I should call this M1G just to keep. Oh, go ahead. What were you going to say?
I don't know what they were going to say, but
Oh.
we have friction to the left.
Friction. You said friction to the left on 1. Let me ask you this.
Oh, wait.
Yeah, you got it,
Yeah,
didn't you?
to the right. Yeah.
All right. Now here's the deal. Here's the book. If there was no friction at all, let's say this was an ice cube, or let's say this was an ice cube and this was Teflon. As I move the book forward, this would fall off the back, right? So as I move this forward, if there was no friction, it would fall off the back. That means friction must point this way on the top object. Otherwise, it would fall off. There's a tendency of this object to fall off the back relative to 2. That means the friction on 1 is opposite its motion relative to 2. That's forwards. If there was no friction, it wouldn't move forwards. There is friction, therefore it does move forwards. Tricky. And then just so we have it, I'm going to label this. It's accelerating this way. Notice I do not draw the acceleration touching the object. Right? Okay. That's a sneaky one, right? Questions about this? All right. Let's go over to FBD2. Okay. Somebody tell me, what do you think?
Now, would this one have the normal force and the normal force for N21?
Yes. So, okay, there's a normal force. Okay, let's start with N21, right? Or N12. Which way does that act on block 2?
Down.
Down. So there's a normal force down. Now, a lot of you might be thinking, wait, shouldn't I just say the weight is acting down? Think about this carefully. Because these two are equal, the magnitude of the object one's weight is pushing down on it. However, M1G is the force the planet exerts on M1. M1G should never, ever, ever be drawn on object 2, ever, ever. Now, in this case, a mathematical trick works out where this normal force is equivalent in size to M1G, and it happens to point the same way. But what if this was on an angle, or if things were being pushed, or if it was accelerating up and down? Normal forces in general do not always equal the weight of another object. What if it's accelerating up instead of just to the right? What if you put this whole thing in an elevator? If you had said N12 equals M1G under almost any other circumstance, you would get the answer wrong. So don't do it. Look, the book pushes up on the drive with a normal force. By Newton's third law, the drive pushes down on the book with a normal force. Obviously, if there was no planet Earth, there'd be no weight force and there would be no normal force in between. But get it right. Okay.
Is another way to look at that, like looking at FBD1, when you do the y equation, N12 equals M1G?
Yes.
Okay.
So we know that on the very next step of the problem, for this case, you could replace this with M1G because of the y equation over here. Absolutely correct. So you might get lucky on test day if this is your question. So I'll make sure this isn't your question on test day. That way, anybody who does that loses points. All right. Just basically, this is the right way to do it. All right. What's another force? Jesse, you said there's another normal force. Which way does that act?
Pointing up.
What do you want to call that one?
Can we call that one just N?
Sure. Right? Isn't that the total normal force? It turns out that's going to be the same normal force here. Do you agree?
Yes.
So in this problem, there's no need to put a subscript 2 on this one because the total normal force happens to also be this normal force. Okay, cool. Anything else? I guess there's a force F. I'll get that. By the way, that's going to be here too. Might as well do this. Isn't this going to be M total G? Whoops. How about this one? What are we? Did we get it all?
That one has friction to the left.
Friction to the left.
And also there's friction between the blocks, but
Between the floor?
No. Right. So there's friction between the floor and between the blocks.
Oh, whoops. Oh,
and you
whoops.
got the one between the blocks.
Okay,
and
so
they're both to the left.
yes.
I think you
Okay.
spoiled it for me, but I got it.
My bad. Sorry. There's friction to the left on both of these, right? So this is friction with the floor, right? That's right here. There's also friction up here between the blocks. Think about it like this. Did we forget the weight? There's
Yeah.
also
yeah.
M2G. All right, so here's the deal. Think about it like this. This friction basically helps you understand why the book is going to be slower when you put this thing on top of it. When you put this thing on top of it, there's a frictional force between them. Obviously, some of that is doing positive work, speeding this thing up, but it's also holding this back, right? The friction from the object on top is holding it back. The road itself is holding it back. Okay. This thing is weighing it down, so to speak. That's what this normal force is. So these two right here, I should probably do those all in purple here. Notice the frictional forces always come at right angle pairs. The friction and normal force are always at right angles in these, but then we flip them because they're action reaction. All right, and I think we've got this all now. Let's take a look at the solution and see if that's a little bit neater and you can ask any questions you want. This is 19.
Yeah.
Okay, thanks. All right. So in this one, it looks like N2 and N total should be the same. Agreed? Wait a second here. There's a normal force missing, isn't there?
On M2G going down.
Yes. Look at this one. There's a normal force missing here. Ah, I got to fix that up. That's funny. I didn't even notice that. But yeah, so I'll fix that up later. Normal
Why are
force.
the why are the normal forces going out to the left and right?
Did I
for
pick the
one?
wrong problem? Oh, that's
Yeah.
18 and a half. Whew. Shit. Oof. There we go. That looks better. Sorry. I guess it helps to get the right problem, right? Okay. I don't know what 45 is. That's just a typo, I think. But all right. So that looks a little bit better, doesn't it? Yeah, there we go. Now we're on it. Sorry. Forgot about that half problem in there. All right. So there's our force equations. From there, you could solve whatever you want. Now, notice this right here. No mention is made of it slipping. We were told that the acceleration was 5.5. So look at this. If we know the acceleration, we can get these frictional values between them, right? So now we don't need this equation because we have the acceleration. If we have the acceleration, we could figure out the friction that way. And that is what is different with this type of problem when you're not on the verge of slipping. And once you get that, the whole problem follows. So again, because we know this, who cares if we don't know that equation anymore? We can use this. Any questions about that? All right. Always good to look at the correct solution number. All right. Let's see where we're at here. Let me just scroll through and show you some fun highlights in this section, and then we're going to move on to circular motion. So just keeping you aware, we're going to take our break 10 minutes before we start the group activity. So about 6:05, we're going to take our break. So if at some point today you got to just quick get some fluids or use the restroom, go do it, and then just come right back. You've got the live stream if you need it, okay? Or hold on for another 50 minutes. Okay. Oh, whoops. I don't want this one. I want this one here. All right. Make sure you do 6.21. I'm sure I put this on your list, but this problem is a good one. A lot of students discover they don't really understand what's going on when they hit this problem, 6.21. So this is a good one to do. All these are good. 6.24 is another fun one. I'm sure these are on there. 6.25 is a fun concept question that forces you to really deal with this issue. And you could see that once you get to the FBDs, if you draw them correctly, it's easy. The rest of the part is easy. All right, whatever. Here's some graphing questions. I think you guys are going to do a couple of those. There's a weird one where the thing is on the ceiling. You could use that. You're going to see all these. This problem, 6.33, was an old test question too. Almost all of these were old test questions. But this is a weird one where people think because they're connected by a string, I could use them as a system. But I just want to point out, this is not a problem where you could use a system because this one's moving that way. This one's moving this way. As a result, they are not moving together in unison. And the frictional forces between them, it turns out if you did a system, you would think the frictional forces between them drop out. In this unusual situation, friction gets double counted. Anyways, so this is a very weird problem. They're all easy if you follow the procedure of draw each FBD separately. Here's another good one. This is a clever one. Okay. The tablecloth trick. And let's see, let's get to something here. More crap chemistry. All right. Ooh, 6.39 is a classic. How fast do you have to drive before the box slips off the back? So that's kind of similar to what we just did. All right. And now we're up to circular motion. All right. So we're okay. So let me pause. We're about to start circular motion here. Any questions on friction before we move on to that new topic? Okay. Okay. All right. So let's take a look. This is where it gets exciting. So those of you that had me for 110, it's time for things to start changing here. Now, let me start with just a, right? Let me get this up here. So imagine we have this situation here. This is what I was showing at the beginning of class here. Let me scoot this back a little bit and I'll start this thing spinning. So in general, notice circular motion is not just something simple. I don't know if you could see that or not, but this thing is not moving with constant speed. It speeds up as one of the masses gets to the bottom of the swing. It slows down when the other one gets to the top, right? So we need to be able to understand these problems here. This is circular motion right here. It doesn't complete the full circular motion, but it's moving in a circular path. So we want to try and understand the motion of any one of these masses. And then obviously we could even get a case right here. All I'm doing is I'm putting these two right on the outside. In this case, the masses are equally spaced. And so as a result, let me see if I can scoot this back so you can see it just a little better. There we go. So in this case, hopefully you could see that this is moving approximately at constant speed. There's a little bit of friction, so it's slowing down over time. But the idea here is if these masses are balanced, things are going to move at constant speeds. If I make this not balanced, we see this velocity can change as it moves in circular motion. So we're going to study two kinds of circular motion. This kind, where the thing is balanced, would be called universal circular motion, or sorry, uniform circular motion. This is discussed in a page or something, right? But in general, we need to handle both. So we need to learn some notation first. So our goal is to understand these types of circular motion problems. So let's go in here and look. All right. This is the coordinate system we want to use now. You might think, so I'm looking right over here. This is the coordinate system we want to use. It turns out this is very useful where we say r hat, and that means radially outwards, radially outwards. If you're not sure what page we're on, hold on. 111, page 111. Ooh, a good number. Okay, so r hat, radially outwards. Okay, theta hat. Theta hat means in the tangential direction, so tangent to the circle. In a math class, they always choose counterclockwise. Well, we're physicists. Sometimes we might make this direction theta hat. If everything in the problem is rotating in the negative theta hat direction, physicists flip the theta hat coordinate. Why not? Sometimes we might describe a direction this way. I would call this towards the center. So I might call that C hat or centripetal hat. The word centripetal itself means center pointing, centripetal, center pointing. So there's different coordinate systems here. More on that in a minute. Our first real problem, we will go into all the details on coordinate systems and the differences. So for now, let's just ignore them and focus on r hat and theta hat. Now notice this here. Here's r hat, cosine theta in the I hat, and you can label this yourself. And this is sine theta in the I hat, right? What is the magnitude of r hat?
Is it 1?
1. What's the magnitude of any hat vector? 1.
1.
So, but check it. Cosine squared plus sine squared, square root, equals 1. Cool. So this seems reasonable. This is a plausible way to write r hat. So notice if you go up some angle theta, we could describe r hat in terms of I hat and j hat this way. What about theta hat? Notice it goes to the left. So we get a negative sine theta here. This is the minus sign, sine theta to the left. And then cosine theta up. Notice sine squared plus cosine squared equals 1. Take the square root, you get 1. Also, maybe you could see this. There's a right angle here between these two. Help me out. What is r hat dot theta hat? What's the dot
Zero.
product? 0. The dot product between any two perpendicular vectors is 0. Take a guess what r hat dot r hat is. What's any hat vector dotted with itself? Rhymes with
1.
none. Yes, 1. Theta hat, right? So any vector dotted with itself, any hat vector dotted with itself. What about this? What's r hat cross theta hat? Let me give you a hint. This is I hat. This is J hat. What direction is K hat? Into the page or out of the page?
Out of the page.
Out of the page. What do you get when you line up the fingers on your right hand with R hat, curl them to theta hat?
Out of the page.
K hat, out of the page. So, okay, now to be honest, we focus on this stuff a lot more in Physics 163, but I just wanted to point out this is now, if you are a mechanical engineer, this is your bread and butter. So you had better know this stuff if you're a mechanical engineer. So you will take a class called dynamics where you study these unit vectors in great detail. You can worry about it then. For now, let's just point out that r hat and theta hat mean these directions. Focus on this. R hat and theta hat, what they mean. Okay. Now, here are some definitions you're going to see me use. Clockwise, sometimes I just get lazy and say CW, CCW for counterclockwise, period. Okay, this is the time to complete a single revolution. So I try to write it differently than a capital letter T because we might have tension, right? V subscript tan is called tangential speed. It's the speed of the ball at any point in its motion. And A tan is called the tangential acceleration. Let me give you a visual on this one. Let me clear everything here. Okay, here's a ladybug moving in a circle. For right now, let's do simple circular motion, meaning uniform circular motion. Constant speed, right? And we could even look at this. We could see the velocity. We could see the acceleration. Notice they're always perpendicular. Now, if I just pause this for a split second, hopefully you see the velocity is tangent to the curve. That's why we sometimes call this V tan. Okay. And notice in this case, this acceleration is pointing towards the center. Now, here's where people get a little confused when they read books sometime. We are going to learn that AC is given by speed squared over the radius. Okay. Now, in this case, notice that the acceleration vector in this case would equal AC in the negative r hat. Take a second and make sure you believe that. The acceleration is in the negative r hat direction with this magnitude, this AC magnitude. Okay. So in this case, what happens if we do this in an ellipse. Now look what happens here. When it's moving in an ellipse, I just want to point out, sometimes the acceleration and the velocity are not perpendicular. Because in this case, the ladybug is speeding up and slowing down. Right now, based on what you see here, I don't know if you could tell, is this ladybug speeding up or slowing down at this instant?
Speeding up?
That's right, because there's a component of acceleration towards the center of the circular motion, right? You could view this as being a circle of this radius, even though at any one point you could pretend the motion is circular, even though it's moving in an ellipse. So there's an acceleration component towards the center, but there's also one tangent to the curve. This is why we sometimes call this a tangential. So there's different components here. We could say this is AC and this is a tan. Now, even crazier, check this out. What we could do, whoops, we could actually move this around, and this is circular motion too. It's just a weird circular motion where the radius is constantly changing, right? So almost any motion can be viewed as circular motion as long as you're willing to accept the radius of the circle is changing while you're moving. And so what we want to do is figure out, you could even flip directions here and go the opposite way. It's still circular motion. It's just a very weird circular motion where the radius is changing and the direction is changing all the time. So weird, right?
Do you have to like assign a position or somewhere to base off your radius, or how would that work?
Yeah, so what we would do is R, so this, a short way to say it would be, now this is complicated motion. So usually you handle this in a dynamics class, but the idea is, in this case, this is where it gets really complicated. R is a function of time. But the problem is both the radius and this are functions of time. I hat is not a function of time. I hat is always to the right, but R hat has a cosine theta I hat plus a sine theta j hat. Because the angle is dependent on time, we see that all you'd have to do is figure out all of the theta and R as a function of time. Extremely difficult, extremely difficult. But in theory, you could do it. Is that good?
Yeah.
And then you could take derivatives to get the velocity. Notice when you take derivatives in circular motion, sometimes you have to take derivatives of the unit vectors as well. That you will learn about in a dynamics class. So if you're a mechanical engineer, take dynamics and learn all this then. Otherwise, we'll never get, whoops, oh shit. Hold on. Messing up my house. All right, whatever. I'll build a school. All right. Let's see. Where were we here? Okay, here we go. Here's something you got to watch out for. AR versus AC. So if I look down here, I'm looking at these two equations at the bottom. Notice there's a subtle difference. AR has the minus sign inside of it. AC is the magnitude of it. So just like we did a lot of problems where we said AY was equal to negative G. G was the magnitude of the acceleration, but AY was the acceleration. Similarly, AR equals negative AC. And so when you're reading books, the absolute value of those two is the same. Okay? But we got to watch out here. Strictly speaking, AR is a negative number. AC would be a positive number. Notice I said this like 4 times. That's a very common misconception that they're the same thing. They're not. All right. Okay, let's look at a problem here. Let's go down to here. Here we go. 6.47. This is just the next page, 112. Let's look at this one. Let's try to get a feeling for this. So we know that A is related to the change in velocity over the change in time. Well, what's delta V? What does that mean? What minus what?
V final minus V initial.
Yeah, final minus initial. So if this right here is V initial, hopefully it makes sense that that right there is negative V initial. It points the opposite way. Okay. So what is V final in this problem is going like this. Negative V initial is going like this. Notice delta V, oops, I forgot the vector symbols. Delta V points this way, right? In this problem, that's right towards the center. Take a second and see if you believe that. Just before it hits the top, it's moving upwards. Just after it hits the top, it's moving downwards. The horizontal components have basically not changed at all. The change is entirely in the vertical direction. There's a force towards the center.
And this is true because of uniform.
This is true anytime you have circular motion. And it's not even uniform. Now, I would say this, if it's not, now here's non-uniform motion. This would be where it's speeding up or slowing down. In these cases, you might expect there's a component towards the center, but there's also a component tangent to there. And so this would be the total acceleration. So to be clear, I'm going to start using some words here. This is AC. This is sometimes called a tan. And the other side would be the total acceleration. Just to keep it straight, we sometimes put a subscript total on this. And sometimes we just say A. But you might hear me say the words total acceleration. So there's still a component this way. Alonzo, is that good?
Yeah.
There could be other components as well. But so in uniform, it will always point straight towards the center. In non-uniform, it might be pointed a little bit to the left or right or something. So going back to what I said here, you may want to label this right here. These right here are A total. So you may want to put that information in your lab notes or in your whatever you call it, A total. Got that? That's A total. Okay, sorry about that. Good. All right. Let's do a quick problem here. Here we go. Let me find it now. Whoops, let me do this. Let's say we have this pendulum here. It's swinging back and forth like this. And what I want you to do is take a minute to figure out which way the centripetal acceleration is pointing and which way the tangential acceleration is pointing as this thing swings back and forth. And we're going to start right here, and we're just going to go all the way across. So if it helps, this is in your workbook on page 113, problem 6.51. So just figure out which way you think the tangential acceleration and acentripetal are pointing in this problem. All right? And I'll give you a minute to think that through. Again, we're orbiting this way, so it's going across. It starts from rest. And then it reaches the other side. It comes to rest again at the top. So during that first swing, as it goes across, what should happen? Where do you think the centripetal acceleration points? Where do you think the tangential acceleration points? How big is it? Let's take a minute. All right. So hopefully you've had a second to think about it. And let's go to this simulation to do this. Whoa. Let's clear those animations. So let's say we start right here, right? Initially, what is the centripetal acceleration right at the beginning?
Directly toward the center.
How big is it? Big or not big?
Zero.
It's
Not
zero.
big.
Initially, AC equals 0. What's the equation for AC? Do you remember?
V squared over R.
V squared over R. What's its initial speed?
0.
0.
Rest.
So that's why it's 0 at the beginning. All right. Is it going to remain at 0 speed, or will the speed change?
Change.
It will change. So this means at the beginning, there must be a tangential acceleration. Which way is the tangential acceleration? Is it this way or that way? It's got to be tangent to the curve, right?
Is it right?
Yeah, it's going to be this one. It's going to speed up. So let's take a look at this one. Notice right at the top, there's no velocity, and it's going to accelerate tangent to the curve. Think about what should happen to that yellow acceleration arrow and the green velocity arrow, which you don't see at all. Right there. Notice now at this moment in time, there's an acceleration towards the center because it's moving. And there's an acceleration tangent to the curve. What's happening to the tangential acceleration? Is it getting bigger or smaller? Can you tell?
Getting smaller.
Yeah. How about the velocity?
It's staying
It's increasing.
constant.
It's increasing. It was 0. Now it's something, right? It had 0 speed initially. So, okay, let's keep looking. As I hit play, predict what should happen as it gets to the bottom. Notice right at the bottom, let me go back here. I'm going to play this. As we get to the bottom right now, notice the velocity is to the right and ever so slightly down. If we go 2 or 3 more clicks, now it's to the right and ever so slightly up. This is that case we just described in reverse. We're at the bottom of the circle now. Velocity is towards the center. But I do want to point out here, right as we get to the bottom, what's the tangential acceleration right at the bottom?
0.
0. Think about it. Right before you get to the bottom, you're not going up and down much anymore. So as you swing left and right, gravity's not going to speed you up at all. So that's why at the bottom of the swing, tangential acceleration goes to 0. And then we see this going back and forth, back and forth. All right. And so that's what's going on. Now let's look at this in pictures, still photos. Oops. Oh, there it is. So you can see I've got all these photos in there for you. You can look at them. But so look at 6.51. This is what's happening there. So that's kind of a still shot. You can see that the total acceleration is never zero. It's constantly changing. But we see at some points of time, centripetal zero, tangent. This is very complicated. All right. Any questions about that? Well, I have this up on screen. All right.
The fastest velocity would be all the way at the bottom, right?
Yeah, generally speaking, like if you're on a roller coaster, we're going to learn about this in chapter 8. When you get to the lowest point on the roller coaster, that's usually when you're going the fastest. Same thing here. When you get to the lowest point in the swing, that's when you're going the fastest. So that's why this is the largest arrow, right? And we will discuss that more in chapter 8 for sure. Is that good, Alonzo?
Yeah.
Right on. All right. Okay. Let's see. Okay, so there's that one. What did I want to say? There was something I was going to say. Hold on, let me think. We're almost up to that problem. What was it? Was it something here? I don't know. All right. Oh, I know what I was going to say. So here's another thing that I wanted to think about. Let me show you this one. No. I want this one. No, I want this one. Okay. So in this case, remember we saw this one already? This was foreshadowing, right? We saw that the marble goes in a circular path. And at this point, right, the velocity was tangent to the circle and the acceleration was towards the center. And so we see, think about this like you being in a car that's rounding a turn. You feel like you're pushed to the outside, but that's fictitious. You are not really pushed to the outside. The car door is pushing you towards the center of the circle. Because you are pushed towards the center of the circle, you move in a circular path. Another example. Okay. In this case, right, when I'm spinning this thing, right, what is the object that keeps this thing from flying around and smashing into my door?
The rope.
The rope. Do ropes push?
No,
they pull.
Tension.
They pull towards the center. So if you're confused about is there a force outwards or inwards, you know this already. If this is going to swing in a circle, the rope has to pull on it. If not, if I let go, it goes flying off into outer space, right? If you're swinging this thing around and at some point you let go, there's no more tension. It's going to move in a straight line. So we've seen this a couple of times now, maybe not very well because it's online, but just try to keep that in mind. There's a force towards the center. There's an acceleration towards the center. You feel, you perceive like you're being pushed to the outside when you round a turn. That's only because the door is pushing you towards the center, so it feels like you're being pushed to the outside. Normally you're riding along and then the door comes on and smashes you into the circle. Okay, very counterintuitive. We'll discuss this again next week. So we've got 20 minutes. We're doing all right. 20 minutes to the break. All right. Whoa, we don't want that anymore. We want, what was it? This one? Whew. Okay, so let's start looking at a real problem because you all know this concept stuff is not the only thing that's on a test. You need to know how to actually calculate something. So let's try and get used to this. And this is our first one. This is page 114, 6.52. We're going to do an FBD. We're going to do some forces. And I'm actually going to show you how you could solve this one with multiple different coordinate systems. Okay, and don't plug in any numbers yet. Let's do this as a group. What is one force acting on the star?
mg down.
mg down. I'm cool with that. There's mg. What's another force?
Normal up.
No. Take a look. So this is one of the things that's very common misconception. Think about this. When I'm spinning this thing around on a circle, is there a normal force holding it up?
Would it be
No.
the tension?
There's just the tension, right? Okay. So it looks just like a banked curve. You want to put a normal force. It would feel so good, but it's not there. So when we get to here, we know that there's mg down and there's a tension towards the center. There is no normal force this way. That is not there. So we've got mg and a tension force. Now, let's look at these equations here and show you why students kind of have to practice these. Let's get to the next problem. Give me just a second. There we go. I think you could see both styles. So I showed you two different styles. A lot of people are used to math class and they want to say, let's say everything's radially outwards positive and things going clockwise, going counterclockwise are positive. If you do that, when you draw the acceleration vector, notice you have to split it up. AC would be in the negative r hat direction. A tan, in this particular case, also happens to be in the negative theta hat direction. Let's look at these purple equations here. Start with the theta hat. We said this is positive theta hat. This would be negative. And that's it. There's only one force in the theta hat direction. This is in the negative direction. That's where this minus sign and this minus sign come from. I'm going to look at the r hat as well. So notice we said this is positive r hat. So notice this is negative r hat. This component down here is negative r hat because it's going towards the center. So I get a negative sign and a negative sign. And notice AC is also going in the negative r hat. So I get a negative right there. Woofda. Why do physicists sometimes change the coordinate system? Gee, I wonder. If you flip them, you get to this one and everything becomes positive. Look, centripetal hat, AC is in the positive direction, tension's in the positive direction, mg sine theta is in the positive direction. All right. And if we flip the theta hat, if I choose to call this theta hat instead, this becomes positive and this becomes positive. So that's why none of these have any minus signs down here. So is this a good way to do it? Not necessarily. Is it a legitimate way to do it? Sure. Okay. So in this case, that's a lot to digest. I'm going to pause for a minute and see if you have any questions about all that junk. I'm going to clear it out. Any questions? Here it is again if you need it.
So why is it a C hat instead of an R hat?
R hat by definition is radially outwards. C hat, I'm choosing to call towards the center. So you could also call this negative R hat. But I chose to call it C hat so I didn't have to think about minus signs. That's it. Cool with that?
Gotcha. So R is because it's pointing away from the center, aka the
Yes.
radius.
By
C is-
definition, R is always away. Oh, go ahead.
Oh yeah, and then I was just gonna say, and then C is because it's pointing towards the center.
Exactly.
Okay.
Cool.
Thank you.
Yeah. All right. Other questions?
So theta hat just points to the direction of the tangent line of that circle at that one point.
Yes. So this was one way to call theta hat. That's the standard mathematics definition of theta hat. This one, I chose to call theta hat this way because that's the way this particular thing is rotating. Just like sometimes we say up is positive, this would be like saying down is positive, right? It's the same thing because it reduces the number of minus signs. That reduces my probability of making a mistake.
Thank you.
Also, oh yeah, this one feels good to me as a physicist. We know that for an object moving in circular motion, there should be a force towards the center. So sometimes these problems are going to get complicated. I know if I do this, this had better be a positive number because this is a positive number and it gives me a way to check my work. Cool?
Good, thank you.
Yeah. All right, now check this out. This gets even spicier here. I'm going to just lower this size just a little bit, just so I could fit it all in here. Notice this. I went in and plugged in some numbers. Okay. So notice A tan, the M's drop out. This is true whether you use a 5-pound ball or a 10-pound ball. The tangential acceleration doesn't matter. I got this weird number. AC, I got this number. Okay. V squared over R. In this case, R was the length of the string. Look at this. The total acceleration is given by this. Notice the original problem. I'm going to show you the original problem for a second. The original problem had 30 degrees in it, right? 30 degrees. All these numbers were based off 30 degrees. When I go back in here and actually look at the solution, notice the actual tangential acceleration has nothing to do with 30 degrees. It's crazy, right? It is what it is. It relates to that 30 degrees through this complicated set of equations. And there's no easy, you cannot just feel good about it. Just accept the facts. And that's the way it is. This is physics. These are Newton's laws. They make this prediction. This prediction has been tested overwhelmingly and confirmed. Weird, right? All right. Let's go back to here. Yeah, there we go. All right. This begs the question. Okay. Oops. Let me get this one in here. Okay. So in this case, whoops, I'm turned around. Oops. We're going to look at 6.53 and 6.54. If I could get those both. It's supposed to look like this. You got to be quiet in here. I'm working. All right. So now in this case, this is supposed to be that model, right? It's a little bit bigger, but I just wanted to point out, you could imagine this is how it looks on like an amusement park ride where they put in some loose coupling here so that these things could swing so that as you go up and down, you don't fall out of the chair, right? So I know it's not perfect. Maybe if I scoot it back even a little more.
Sorry, this is 54.
This is 54 and whatever it is. But yeah, give me just a second. I'm going to screen share. That's what's going on in 54 and 53, basically, right? If you have an amusement park ride, the chairs can swivel, right? And so in order to understand this thing, before we do this, I just want to point out, in this case, because the system is balanced left-right, or right now it's left-right, because I have the same amount of mass on each side, it's not perfect, but it's approximately balanced. This situation is totally, it's totally reasonable to approximate this with uniform circular motion where it's moving at constant speed, right? Obviously there's some friction there, but in a real amusement park ride, there'd be a drive, a motor. And you might say, what about the people being different masses? Well, yeah, imagine these giant metal arms. They're going to dwarf the masses of the people. It would be very similar to this, where you have a very heavy rod and then some small little people at the end. All right. So in this case, we need to understand some terms. We got 8 minutes or whatever, 10 minutes till we take our break. We're good. So in this case, I just want to point out here a few things. The distance around this circle is how much?
2 pi r.
2 pi r. The time it takes to orbit is the period. What is distance divided by time? Think about the units.
Meters per second.
Meters per second. Speed. So this is the relationship you can use. So if you're wondering, how do I get the period? Well, solve this, and what do you get? Uh, 2 pi r over v, is that right?
Correct.
Okay, so there's the period. We are also going to use a symbol called omega. Omega is not W. W is going to be sharp and pointy like this. This is an omega. Omega is a Greek letter. Okay, if you call it W, I'll get used to you saying that, but I'll want to strangle you every time, and I'll say, it's omega, it's omega. So if you don't want to hear me saying it's omega all the time, just start calling it omega. You could tell because it's curvy. Okay, it turns out omega is a number that relates to the period. Some of you are going to talk about this tomorrow in lab, so hopefully this is helping you. All right. Now, it turns out you could also get revolutions per minute. So this is a great problem for you to kind of learn all these basic things. Notice we know 1 revolution is 2 pi radians. There's some simple unit conversions and do it so using these symbols. You could, in theory, use that to attack this problem and understand it. Now, I know next week we are going to discuss this even more. At this point, I want to show you one other problem. We're going to cover a lot of these problems. Maybe you're wondering about how fast you have to swing a bucket of water so it doesn't spill out. Okay, maybe there's this one. We're going to handle this in lab in a week or two. All right, or this one. They're so fun. And then cars going around curves. We'll talk about this in depth. And actually, the one I wanted to talk about was right here. 6.60 at the top of page 117. This is the last one before we take a break. Okay. I also want to make sure you pay attention right now. Hint, hint, this might help you with your quiz. Okay. Or your, whatever you call it, group assignment, whatever you want to call it. So if you're tired, try to slap your face and wake up for this one. Okay. Imagine you have a car driving around at constant speed on a banked curve on a circular racetrack. We will cover this more thoroughly later, but right now we're told the car hits a patch of ice. Friction is negligible at this instant. Let's draw the FBD. Nothing here is crazy. You can draw an FBD. This is still basically chapter 5 because there's no friction. All right. Tell me one force acting on the car. Don't overthink it.
Gravity.
Gravity, which way?
Straight down.
Straight down, mg. Got it. What else?
Normal force,
Which way?
perpendicular to the plane up.
Excellent, excellent. There's no friction. We're done. Which way is this accelerating?
Down the plane, like toward the center of the circle.
What you just said was not commensurate with each other. Down the plane is incorrect.
Yeah.
Towards the center of the circle is correct. Let me help you visualize this by drawing the other half of the curve. This is theta. It's orbiting about this line, right? It's going around this circle like this. That way is towards the center. And now, gone. Notice this starts to be bad if you say to the left for mg sine theta, right? Because AC is to the left. According to every human in the universe, mg sine theta is not to the left according to every human in the universe. So you got to watch, and this is what I was trying to warn you about, G. Does that make sense? You could still do problems however you want, but I want you to be careful about saying to the left. All right?
Yeah.
And yeah, this is when it starts to matter. All those other problems, it didn't matter at all. So watch out for this one. Okay. Yeah. Now, in this case, we could actually, I don't know. Which coordinate system would you use for this one?
The diagonal, because you only have to change the AC, right?
I would actually use, I don't know. Look at this one. So here's the thing. When we start doing these kinds of problems, what if I chose this coordinate system? Straight up and down. I only have to split up the normal force. In this particular problem, it's actually better to use an unrotated coordinate system. Whoa. And in fact, I'm going to kind of foreshadow this. What if you add in friction in the next problem? Let me show you something. Which problem was that? 6.61?
Yeah.
6-0.
So notice this is actually, okay, so this is 6.1 where I added in the friction. And I just wanted to show you, here are two common styles. And they both have advantages, as you can see under here. So this is the issue that you may encounter on your group assignment. Sometimes you may want to use a rotated coordinate system. Sometimes you may not. Sometimes you draw both of them and figure out which one works best. So I just want to give you a second to kind of absorb this. Our free body diagram from 60 was exactly the same. All I did was add in some friction here. So you could just pretend that friction isn't there or just say, oh, okay, whatever, there's a friction. But you could see there is no clear winner here. In this style, I have to split up two vectors. The acceleration has to be split up if it doesn't line up on the coordinate system, right? Over here, the acceleration lines up, but I have to split up two other vectors. You're splitting up vectors no matter what you do. This is how one set of force equation turns out. This is how the other turns out, and that's it. Questions on that one?
Why is it called Z on the coordinate system?
Because in this case, I know this is going to seem a little bit silly, but give me a second here. Whoops. It's kind of hard to do with this. So imagine as this thing orbits around, that's the inclined plane. So if I just do this like this, right, it's very similar to that problem. Now, when I do this at some random shot in time, I think we're at this side, I don't know which, but at some point, this is like the curve, right? Well, this is tangent to the circle. This is towards the center. This is perpendicular to the plane. This is parallel to the plane. This is some other direction. To me, that's going away from the Earth. That seems reasonable to call that Z. Could you call it something else? You could call it frog. You could call it Taco Bell. I wish I had, if you had 1 million tacos in my hand right now, everybody would get an A. But I don't have it. You should have built a time machine. Damn it. I wanted those tacos. But sorry, your question. Did that address your question?
Yeah, so because it doesn't fit a descriptor for anything
It doesn't
else.
fit towards the center. It doesn't fit tangent. It doesn't fit parallel. It doesn't fit perpendicular. Let's call it Chewbacca.
Gotcha. Okay.
Yeah. Cool. All right. So now this is what I'd like to do. I'm going to stop the live stream. We are going to do more of this next week in case you're thinking, oh my gosh, this is going to kill me. Yes, it will kill you. But